Now, question 18. I like question 18. I got to question 18 because when I was tutoring my student, I saw this question on her trial exam, on her practice exam, and I said, "Hey, that's a really good question. I'm going to steal that." And I called the guy who wrote this paper and asked if I could steal that question. And he, we went this question. I really like this. Now, it's really important that as engineers, the most important thing is we want to try and design to eliminate problems. Always our goal is to design to eliminate problems. So if we didn't have answer D there, we might have a different situation. I'll read the question. Which is the best method for protecting metal structures from corrosion? Well, for structures we can galvanize them, that's good. We can use sacrificial anodes. When do we typically use sacrificial anodes? Boats, great. We could use ICCP, impressed current cathodic protection. Pipelines is a good answer for that. Yep. But finally, the best answer here is the elimination of corrosion sites during the design phase. Yeah? That's the most important thing. If we can design things to eliminate corrosion as a possibility, that is our best answer. Okay. This question is an interesting one, right? Now, what we're being asked to do... Question 19. A simple beam is loaded, showed in this diagram. And below, we've been provided with a shear force diagram. Now, it said, at which point will the bending stress occur along the beam? Now, we've got 4 points. A, B, C, and D. Now, at which of these 2 points are possible answers? There's 2 answers that are possible. Which 2? A and C. A and C. How did you know that? Yeah, that's one answer. Yeah. It's where they cross the axis. Now, by this stage, you should be at the point where you've done this in maths, where you've learnt that maximum and minimum points occur when the integral or the derivative crosses the x-axis. Yeah? You've learnt that? Okay. So, as a result, we only have 2 areas that we need to look at. We need to look at the area that goes from the end of the diagram to A, or we need to look at the area that goes from the end of the diagram to C. Now we can choose which side of the diagram we want to look at. We don't really care, but we can go from either the end of the diagram to A or the end of the diagram to C. For the sake of this being quicker, I'm just going to find the area of this rather than finding the area of all this. And I'm going to find the area of the block that's between C and D rather than finding all of the left-hand side. But just to make this point really clear really quickly. Okay, if we're trying to find the area of block A, right, from the start of the line to A, this blue area is the same as this area minus that area. If you do that, you'll find that you'll get the same value. On the other hand, if you go from here, if you're trying to find the area between C and D, the area between C and D is equal to the A block minus the rest of the minus the area below the diagram. These 2 areas are the same. Yeah? So what we're doing is we're comparing N to A and we're comparing C to the end. Why do we know that we only need to look at those locations? Because that's where it crosses the axis. Okay. For A, the value is 4 meters times what force? 4 meters times what force?
3 kilonewtons.
3 kilonewtons. Thanks, Harry. Okay, so 3 kilonewtons times 4 meters is going to be what? What's the value going to be? 12 kilonewton meters. Okay. Oh, yeah, you're right. You're right. Sorry, the height of the graph, yes, the height of the shear force diagram. Thank you. Good catch. Change that to an 8. Yep. Now this black area would also be an 8. Now for the other side, between C and D, the height of our shear force diagram here was 5 kilonewtons, and it was how wide? 2 meters. So what's that value? 5 times 2 is 10 kilonewton meters. Now, I can look at that and I can know straight away that 10 is bigger than 8, so it has to be the distance from C to D. So at the point C. Yeah? Now, I'm going to do this properly. I lied. I said I was going to do it the quick way only, but you know what? I'm going to do it properly. What I'm also going to do is I'm going to do all of the points on the graph. Right? So we've already found that the value here is 8, and we've found the value here is 10. We already found that. Yeah, we've already found that. Now, okay. What I need to do is I need to find out how do I get from 8 to this 10. Okay, so let's tell the story of some areas. Once upon a time there was this area and it had 8 kilonewton meters in it. And then it came along to another block. And this block was -1 below the line. And how wide was it? It was only 2 meters wide. So the value of that block was 2 times -1, -2 kilonewton meters. So the value that was originally 8, it now lost 2, and it was now 8 minus 2, which is 6. Okay. Then it came across this next block, and the next block, it was -4 deep. And how wide was it? It was 4 meters wide. So it was -16 kilonewton meters. So it went from 6 kilonewton meters, and it went all the way down. 6 minus 16, 6 minus 6 is 0, and then 6 minus the extra 10, it took it down to -10. Now, we had 2 values that were really important on this graph. When I said before that when you do calculus, when you pass through the x-axis, you have a maximum minimum. We don't know if it's going to be maximum or minimum. In this case, we have a maximum of 8 and a minimum of 16. But which value are we most interested in? The maximum bending moment, we are most interested. We don't care, we take absolute values. When it comes to bending, we just want absolute values. Yeah, the maximum bending moment in this case is going to be the -10. That's when we take the maximum values. Right, that's the answer I'm giving, and anyone else who says otherwise is an idiot. Yeah, because when we're designing for steel, we don't just say, oh yeah, but the steel wasn't bending the other way, so I'm sorry that your family is dead, but you know, it was a negative bending moment. I'm sorry, like that's not my problem. I only deal with positive bending moments. Yeah, that's not how we deal with things, right? We have to deal with the either direction, if it's bending up or down. Okay. I'm interested to see what the HSC did actually say for that one. Okay, question 20. It's basically the same idea. It's the same concept that we just talked about. Right, but this time we have to draw the shear force diagram. Just because I rubbed out a diagram that's going to be relevant for people listening on the thing, I have to draw this one again. Okay. I really probably should have written the question number, but anyway, it'll be fine. Okay, finally we get to question 20. Okay, question 20. First of all, we're going to draw the shear force diagram. Okay, you don't have to draw the shear force diagram, but I'm going to draw the shear force diagram. That is the typical way, even for something that I knew was an easy design load, a design case. In all of my designs, if I show you my professional designs that I did, when I worked as a designer, I would always draw the shear force diagram, even if it was a PL-on-4 simple point load. Right? I would draw the diagram so that way I'm communicating information to the people who are going to come after me. The people, when someone does die and they say, let's have a look at Luke's notes, they can go through and they can read what it says. Now, first of all, what do we got here? It goes, we're going to tell the story of the forces, right? First of all, the force went up 9.4 newtons. And then it went across 3.5 meters. Alright, dum. And then, all of a sudden, it went down 8. Right? So it went down 8. What did we have left? Went down 8. What we want now? 1.4. Thanks, guys. And how far did we go across? Well, this time we only went across 3 meters before something else happened. And then we went across 3 meters, and then we went down 12 newtons. So we went down 12 newtons. How far did we end up below the line? 10.6, because don't worry, in the end, we went up 10.6 and it all worked out in the end, yeah? Yay.
It went across 3.5.
Yeah, and it went across 3.5 meters, yeah. Okay. Now, we could find our maximum bending moment. We know our maximum bending moment is going to be where we cross this line here. And we could just say 3.5 times 10.6, bam, got our answer. Yeah, we could do that. We could do that. I'm going to do it the hard way. Why? Because I'm a sucker. Right? First of all, this is like the meta story. This is like we had a story about Goldilocks, but then we're like going to go deep. We're going to like learn about, German society, pre-industrial German society, and child slavery and whatnot. Cannibalism. Okay.
Wait, is that actually what?
I don't think so. Okay. Okay. First of all, what was our first area?
9.4 times 3.5.
Good job, guys.
Is 32.9.
Thank you.
No worries.
Okay, what was our next area?
1.4 times.
Okay.
Oh, no. Yeah.
Yeah, we're going to go 32.9 and we're going to add on 1.4 times 3. 1.4 times 3
4.2.
is 4.2. So 32.9 plus 4.2 is 37.1. Now, how do we know that we went up and not down?
Because it's above the x-axis.
Because it's above the x-axis. Great. And then finally, this part here, it should be 33.5 times 10.6. 30. In the end, it was a happy end. It all worked out in the end. Yeah.
So it's the answer A? Yeah. It's not. It was A.
I
Hey.
got it wrong.
Okay.
I said I got it correct.
Where's my paper?
I swear everything you changed.
Is there a tick next to it?
Yes, it's right. A's right.
Yeah.
There's a tick next to it on the answer.
I-
question.
You know, just D this. You changed.
How long till Bill?
Oi.
3 minutes.
Come on.
Yeah.
We're going to stop there.
Well,